Hello, this is Gregory Maxwell, and in this lesson we will talk about transformations of functions. These will be horizontal and vertical transformations, including reflections, translations, uh, stretches and compressions, both vertically and horizontally. And we will also do a little discussion about the absolute value of a function. Now, let's do a quick review of, it's an overview, sorry, of what the types of transformations we're going to be dealing with in this lesson. So in this lesson, we'll be talking about vertical transformations and horizontal transformations. As a general overview, vertical transformations are related to changes in the y values, and so they affect the range but not the domain. And those typically are up and down movements. And when it relates to functions, they are typically intuitive. That means they do what you expect. So that's vertical transformations. Related to y values, affects the range. They are changes that are up and downward along the y-axis or in relative to the y-axis, and they're typically intuitive when you're dealing with functions. Horizontal transformations deal with changes in x values. They affect the domain, and sometimes, in some cases, they will also affect the range, depending on the transformation. They have to do with left and to right changes because those are along the x-axis, and they typically are counterintuitive as it relates to functions. Here are a few examples of vertical transformations. Adding a number to the function value. So when we add a number, we shift up if the number is positive, shift downward if the number is negative. Vertical stretches and compression means you're multiplying by a number, a non-zero constant. A non-zero constant. If the constant is positive, if you multiply by a constant that's bigger than 1, larger than 1, then you have a vertical stretch, but if it's smaller than 1, you have a compression vertically. If you multiply by -1, if the constant you multiply by -1, then you have a reflection about the x-axis. That's a vertical reflection over the x-axis. And then if you do the absolute value of a function, that has a combination of a reflection and the keeping something static, as we will discuss later on. For horizontal shifts, when you're adding to the x values before you plug it into the function, you have a horizontal shift. If you multiply the x value before plugging it into the function, you have by a non-zero constant, you either have a compression or a stretch, which is called an expansion. And then reflection is when you replace all the x's with -x. That's the reflection about the y-axis. And we will also discuss briefly what happens if you take the absolute value of the x value first before you plug it into the function. Now, let's start off by looking at our function that we'll be working with. This function is a function I got from the Algebra and Trigonometry textbook by Michael Sullivan, 6th edition. And this function is described below. It's a piecewise defined function, y equal f of x. It's equal to 1 for values of x between -5 and -1 inclusive. Then between -1 and 3, the value of when you do -x, so whatever you plug in, you get the opposite number, the negative of that number. And then for numbers from 3 to 4 inclusive, we plug them into the equation, the expression 3x minus 12. So what we have is a constant function from -5 to -1 along the x-axis. Then from -1 to 3, that's between -1 and 3, that's the line y equal to -x. And then from 3 to 4, you're going for numbers between in the equation 3x minus 12. That's a straight line. If you plug in 3, you get -3, and if you plug in 4, you get 0. So this is the function here. As you can see, the domain of this function is from -5 to 4 inclusive. Lowest x value is -5, highest x value is 4. The range, the lowest y value is -3, the highest y value is +1 inclusive. So it's from -1 to 3 brackets. There's one y-intercept which is at the origin 0, 0, and there are two x-axis. It takes two x-intercepts that's at 0, 0, and 4, 0. Because of what we're doing here, we've chosen a function that does not have symmetry. From here on in this lesson, we're going to treat the original function as a dashed red line, and the new result of transformation as a solid blue line. So let's move on here. So the first type of transformation we're going to talk about is a vertical shift. A vertical shift. Now, a vertical shift occurs when you add to the whole function, when you add to the y values. So y equal f of x is the output. If you add a constant to the output, then that changes the function in an intuitive way. It does what you expect. The domain doesn't change because you're adding after you plug in your x's, but the range gets shifted upward by how much k is. If k is a positive number, you go upward by k units. If k is a negative number, you go downward by the same size, the same amount. So basically, we're adding k to the outputs. If the function was an even function, then the function will remain an even function. But if it's an odd function, that's likely going to change. If, as we say, if k is positive, the graph moves upward. If k is negative, the graph moves downward. So the new blue graph in this example, y equal f of x plus 3, our original dashed red line graph here is moved up 3 units. So the minimum value now is no longer at negative 3. The minimum value is now 0 because we added 3 to everything. The maximum value is no longer 1 but 4. The domain doesn't change, however. The y-intercept is no longer at 0. It's now at 3 because we shifted everything up by 3 units. So the domain remains the same, but the range gets added 3 to every value. So the shape gets shifted up. As you can see over here, this is the reason for that. Basically, what we've done is added 3 to every y value. So now the function gets changed. The new output for the top piece is 4. The new output for the middle piece is negative x plus 3. And the new output for the bottom piece is 3x minus 12 plus 3, which is 3x minus 9. So that's the whole result there. So when you add a positive number to the y values outside of f of x, you move the function up by that number of places. If you add a negative, you move downward. A horizontal shift, on the other hand, is somewhat different. There are some similarities, of course. There's a shift going on. However, what you're doing is you're adding to the x's before you plug them into the function. And because you're adding to the x's before you plug them into the function, what ends up happening is the graph gets shifted in the opposite direction. Let's see what happens here. Over here, we have y equal to f of x minus 2, which means we're replacing all our x's with x minus 2. So if I replace all my x's with x minus 2, I'm replacing all my x's everywhere with x minus 2, including in my domain restrictions. So when the original domain said go from negative, x goes from negative 5 to negative 1, x minus 2 should go from that because I'm plugging in, I'm subtracting 2 from the x's before I plug them into the function. And this function only takes inputs of certain x values. In that region, it takes x values inputs that go between negative 5 and negative 1, which means when I subtract 2, I have to adjust my x coordinates first to plug them into the function. So adjusting the x coordinates by subtracting 2 means the x values that I can plug in are now going to be shifted to the right, because what I have is x minus 2 is supposed to be between negative 5 and negative 1, which means x has to be between negative 3 and 1, and I achieve that by adding 2 to all 3 parts to know what x values I can plug in. That means the region that would normally output to 1 now is shifted over 2 units to the right because of the adjustment. Likewise, when I replace all my x's with x minus 2, the whole function gets shifted to the right again. So when I plug in 1, I get negative 1, and I get 1, and when I plug in 5, I get 3. The whole thing gets shifted to the right. Likewise, I replace my x in the bottom part with x minus 2, all the x's everywhere. So I replace each x with x minus 2, and what that does when I simplify and adjust my domain restrictions, the whole domain gets shifted to the right. So when I add a positive x value, I'm going to shift to the left. But if I subtract a positive value, I shift to the right. So the domain then is adjusted by subtracting k from each value of the domain. If k is a positive number, I'm actually shifting to the left, and if k is a negative number, I'm actually shifting to the right. The range doesn't change. The symmetry usually is messed up, but depending on the function and what we add, so symmetry is not preserved. And again, if k is positive, if you're adding a positive number, the graph shifts to the left, and if you're adding a negative number, your graph shifts to the right. That's what we say is counterintuitive. So f of x minus 2 means the whole graph of f of x, the original graph, gets shifted to the right 2 units. Now let's talk about a vertical stretch and compression. Vertical transformations, as I said, are intuitive. They do what you expect. And these are changes made to the y values. So what we're doing here is multiplying every y value by the same number. So if we're doing, for example, y equal to 2 times f of x, that means we're multiplying every y value by 2. Of course, if you multiply 0 by 2, you get 0. So whatever point is on the x-axis remains there, but everything else is stretched like a rubber band. So it's like you're holding the points on the graph, on the on the x-axis the same place, but stretching everything else by, in this case, a factor of 2. Of course, that means the domain doesn't change, but the range is going to be stretched by whatever number we multiplied by. The symmetry will be preserved, both origin and the y-axis symmetry. But remember now that if you're multiplying by a number that's smaller than 1, the graph is going to be squeezed down because everything is going to be a fraction of its original size, a smaller fraction than 1. And if we're multiplying by a number bigger than 1, everything will be stretched by whatever factor it is. So the domain stays the same, but the range gets stretched. And there we have an example with a visual example from our original function. Now, horizontal stretches and compressions are trickier. Again, remember, just like with the addition, we're changing the x's before we plug them into the function, so we have to make an adjustment. So in this example, for y equal to f of 2x, it means I'm doubling the x's before I plug them into the function. So therefore, the x values that I can start out with should be half of what I could have normally done. So to illustrate that, what we do is we go into the function and we replace all our x's with 2x. And then that includes in my domain restrictions. I solve for x and I see that my domain restrictions are half what they were before. So the graph gets squeezed in. And again, it's because of an adjustment. I have to first double the number before I plug it into the function. And when I plug it into the function, then the output indicates. So the domain gets divided by k. If I'm multiplying by a number smaller than 1, then the domain is going to be tripled. If I multiply by 1/3, for example, if I multiply the x by 1/3, then the domain will be tripled because that's dividing by 1/3. Dividing by 1/3 is the same as multiplying by 3. The range doesn't change and the symmetry is maintained. But remember, if you multiply the x values by a number smaller than 1, then you'll have a stretch horizontally. And if you multiply by a number bigger than 1, then you'll have a compression. It's going to shrink in by a factor of 1 over that number. All right. And here we have an example with the graph. Now, these two next ones are both intuitive because there's basically only one thing you can do. And these are reflections. Reflection about the x-axis and reflection about the y-axis. If you put a negative in front of the y values, all the positive y values become negative and all the negative y values become positive. So the domain is going to stay the same, but the range is going to be flipped. The negative domain, the negative region becomes positive and the positive regions become negative. And I see that there's a little error here because that thing should be negative 3 to positive 1. So, sorry, it's going to be, sorry, I see that is correct. Forgive me for that. The range got flipped. While the range was originally from negative 3 to positive 1, now the new range is from negative 1 to positive 3 because that's the negative of the original range. So all we're doing is changing all the y values to negative. The x values do not change. So what was below the x-axis What was below the x-axis is now going to go above the x-axis, and what was above the x-axis is now going to go below the x-axis. And of course, -0 is 0. Likewise, when you're reflecting about the x-axis, when you change the x-coordinates to their negative, you have a reflection about the y-axis, a horizontal motion. So the range, the domain is going to be reversed now. So since I have to change the signs before I plug them in, I have to replace all my x's with -x and solve for x, and then you see that the whole range, the whole domain gets reversed back, reversed. Everything that's on the right side of the y-axis goes to the left side, and everything on the left side of the y-axis goes to the right side. It does maintain symmetry, but it's a reflection about the y-axis when you replace all your x's with -x. This one is intuitive. It does what we expect. And now for the more challenging examples here, we're now talking about absolute value. What happens when you do the absolute value of the function? When we do the absolute value, when we do the absolute value of the function, all the positive or non-negative regions will stay the same. The domain is not affected, but what does change is the range. All the negative regions are now going to become positive. So the part that's below the x-axis is now going to be reflected, because when you take the absolute value of a function or of a number, if the number is positive, it stays the same. If the number is 0, the absolute value is the same. But if the number is negative, the absolute value is the positive version of that number. So the absolute value of -3 is now +3. The absolute value of -2 is now +2. The absolute value of -1 is now +1. So the absolute value of all the negatives are now going to be the corresponding positives. And the effect of that on the function is that it changes it dramatically. All the parts that were below the x-axis are now going to be above the x-axis, and all the parts that were above the x-axis stay where they are. So the function only reflects part of it, and that may very well destroy symmetry if it has origin symmetry. But if it has y-axis symmetry, that will stay the same. The domain doesn't change, but the range will only be the positive versions of the results. Now, let's talk a little bit about the next type, which is absolute value of f of absolute value of x. Now, this one is much more tricky. You have to pay close attention. So the domain of the function is going to have to change, because when we find the domain of the function, we can only plug in numbers that work in the original domain. So in this function here, for example, the original domain went from -5 to +4. But when I take the absolute value of -5, I get +5. But when I plug it into this original function, that gives me no result, because that's not in the domain of the original function. So what I have to do is take the absolute value and only use the p's that will work in the original function. So since the only positive part of the function that works in the original function is from 0 to 4, when I take the absolute value from -5 to 0, the region from -5 to -4, that will have nowhere to go. So that part will not work in the new transformation. Only the part from -4 to 0, because that has a corresponding component that works in the original function. So what I've done is forced this function in this case to become an even function. It's a somewhat tricky situation because the range is also affected, because the only part of the range that works is the part that corresponded to the positive inputs. The part that corresponded to the negative inputs will not be an output anymore, because I change all my inputs into positives, plug them into the function, so it will give me the positive version, the part that would have normally worked. And it's indicated over here. When I do the absolute value of -x, the x values can only work from 0 to 3, and from 3 to 4. Any part that works outside of that region doesn't work in the function, because when you plug in a number greater than 4 into this original function, you will get no result. A couple of things I want to say before we go to some examples. In the case of horizontal transformation, remember to replace all your x's with the transformed value. So in our original function, these are my x's. But if I do f of 2x, I replace every x everywhere. I replace every x everywhere with 2x, and then I simplify. So bear that in mind when you're making this transformation. Next, and this is just a brief point here, it is best to draw the graph of the transform function before you determine the new domain, and also to determine the range. If you can visually see it, it will help you quite a bit. And sometimes you may need to graph it on a graphing instrument, like a graphic calculator. However, sometimes that doesn't work, so you might want to make a graph on paper. Now, this part here, this section is an approach we will use when we're doing our own transformations as well. It is best to do a little arrangement. So typically, when doing transformations of functions, it is best to rewrite the function in terms of a fundamental function, such as those that we've learned in a previous course: x squared, y equal x, square root of x, cube root of x, x cubed, absolute value of x, e to the x, f of x, log of x, or ln of x. So knowing what a fundamental function you're starting out from will definitely help. Then you will also want to rewrite this function in a particular form. What you want really is to get the coefficient of x to be 1. If x has a coefficient other than 1, you want to factor that out and then do the afterwards. So we're going to, if there's when we do the examples, we'll see what I'm talking about more clearly. So if you have a non-zero constant multiplied to the x, you factor out that non-zero constant, and then you do your multiplication transformations first. So in this case, we will do all stretches and reflections first, and then we'll do shifts last. We can do either horizontal or vertical shift last, or you can do vertical or horizontal stretch first and reflections. It doesn't matter. Just do the multiplication transformations first, and then the addition transformations last, like PEMDAS shifts. All right, unless of course they tell you what order to do the transformations. So what we're going to do now is we're going to do an example in which we're going to match the function to its corresponding transformation. So what we're going to do first is look for whichever graph has an original function. As you can see here, there are two basic functions here, two parent functions. And by the way, this is an exercise from the Algebra and Trigonometry by Sullivan 9th edition, section 3.5. So as you can see here, we're looking for the x squared graph, and we're looking for the absolute value of x graph. So the x squared graph kind of looks like this one here, and the absolute value of x graph kind of looks like this one here. So let's start off with the first one. If we have x squared plus 2, that means we took the x squared graph and shifted it up 2 units. So we're looking for the graph that shifted up 2 units, starting with the x squared graph that looks kind of like this. And we see this one is shifted to the right, this one is reflected upside down, and this one looks like it fits the bill. We shifted this graph up 2 units, so that graph corresponds to equation A. Now, for equation B, we see there are two things here, and remember, we do the multiplication transformations before the shifting. So what we did with this graph is we first reflected it over the x-axis, because we are doing it after the x squared is done, and then we shifted it to the upward 2 units. So first we reflected it over the x-axis, then shifted up 2 units. So we have to look for a graph that is reflected above the x-axis, an x-squared graph that is reflected above the x-axis. We see that this graph is reflected above the x-axis, and this one, but this one is the only one that's shifted up 2 units. So therefore, graph B corresponds to number 7. Since these graphs seem to be absolute value graphs, let's continue with the x-squared graphs. Graph E. In this case, we're subtracting 2 from the x's before we square. That means we're adjusting the x values. That's a horizontal transformation. And since this is a horizontal transformation, it's typically counterintuitive. So since we're subtracting 2, we're actually shifting the graph to the right 2 units. So we start off with the x-squared graph, and then we shift it to the right 2 units. And that graph would have to be this graph, not this one. This is shifted to the left, plus it's reflected. So this should be the correct graph right here. So that's graph E. With this graph, we're doing 2 things. First, we're reflecting it over the x-axis, because we always do multiplication transformations first. And then we're shifting that graph to the left, because it's counterintuitive. So we're looking for a graph that's reflected, so it's upside down and shifted to the left 2 units. And the graph that fits that, of course, is number 15. So number 15 goes with F. Now, I is simply stretching by a factor of 2, a vertical stretch. It's going to get narrower because it's like stretching a rubber band. So when we plug in 1 now, instead of getting 1, we get 2. When we plug in 2, instead of getting 4, we get 8. So that matches up with I, and with J, we're also stretching as well as reflecting. So we're doing both a vertical stretch as well as a reflection over the x-axis. And of course, that corresponds to number 16. Reflect it and stretch it. Now let's go over to the absolute value. And I would recommend in this case that you try the absolute value now on your own, because it's very similar to what we just did with the x-squared graph. So in this case, we're starting with the absolute value graph, and we're adding 2 to the whole thing, which means we're changing the y values, we're shifting up by 2. If we make an adjustment inside the absolute value, then we're adjusting the x, because we're doing it before we apply the absolute value. If we do an adjustment outside the absolute value, then we're doing it after we plug in the value, so we're changing the y values. So we start with x, absolute value of x, and shift it up 2 units, and that is this graph right here. That is number 14. That corresponds to equation C. In this one, as before, we're first going to reflect it about the x-axis, so the graph is going to be flipped upside down, and then we're going to shift everything up 2 units because it's added outside, and we do the addition transformations last. So in this case, you see the graph is flipped upside down, but it's not shifted upward, it's shifted to the left. That's not what we want. This one is not shifted at all. This one is shifted upward. The other 2 are not reflected. So the graph that matches here is number 10. Number 10 matches with D. And then G, we are adjusting the inside the absolute value first. And this one, we're subtracting 2 from the x's. Since we're changing the x values, it's counterintuitive. So really, we're shifting to the right 2 units. So we're starting with absolute value graph as normal, and then we're shifting that graph all the way to the right by 2 units. And that graph would correspond to number 17. That's the only one that's shifted to the right. So that number 17 goes with G. Then we are going to look at the next one. This one here, I'm going to just do a little justification down here. We're going to do 2 things, but first we want to do the multiplication transformations. We're going to reflect it above the x-axis because we're doing it outside the absolute value, and then this plus 2 means we're going to shift it to the left 2 units. So first we reflect, then shift to the left. That's what happens with number 9. So that graph is H. And then for K, we're multiplying the whole thing by 2. So we're just doing a vertical stretch by a factor of 2, just as we did with the x squared graph. And in this case, K will simply be number 18. And of course, number 13 is first a reflection about the x-axis. Accompanied by a vertical stretch by a factor of 2. And in this case, you could do the stretch and then the reflection, or the reflection and then the stretch. It does not matter which one you do first, because both of them are multiplication transformations. So L corresponds to number 13. So there we have a nice series of examples for the graphs. Hopefully that is clear. I recommend you go back through these step at a time. Let me just make a little adjustment to my illustration here so that we see that the stretches, the reflections are about the axis. I'm going to use a different color here for the axis. I'm going to use the blue for the axis so that you can see that the reflection is about the axis. So just pardon me for a minute here while I just make this adjustment for the sake of clarity. And of course, in all these cases, we end up reflecting about the x-axis because we only put a negative outside of the main portion. We didn't do a negative x. And when we go to the next examples there, we will see us doing that with a negative x. Now, here we have a series of additional examples. And so we're going to do a few of those. And we are going to, it's very simple actually. We're just going to simply do what they tell us to do. So in the numbers 19 to 26, we're starting with the x cubed graph. And for number 27 to 30, we're starting with the square root of x graph. So let's see how we do those. Number 19. So we have y equal x cubed, and the graph says shifted to the right 4 units. Now, since it's to the right, that means we're adjusting the x values. So we're going to have y equal to, we're going to adjust the x's, and it's a shift. So it's a shift. So we're either adding or subtracting, and then we're going to cube it. Now, since it's to the right and changes to the x's are counterintuitive, we're going to subtract the 4 units so that we'll end up to the right. Number 20, we're shifting to the left 4 units. Same deal. Since it's to a left-right shift, we're changing the x values, but to the left means we're adding 4 units, and then we cube the result. Vertical transformations like shifting upward are intuitive. So we start out with the original function, and then we just add on whatever we're shifting by. And if we're shifting downward, as in number 22, we start with the original function, and then we take off what we're shifting down by. Reflection about the y-axis. The y-axis is like this. So we're basically doing a horizontal shift. A horizontal shift. Let me redraw that right here. So it's a shift this way. So that means, since it's a horizontal transformation, we're adjusting it to the x's. So we're replacing the x with negative x and cubing that. Now, since this is an odd function, it just turns out to be the same effect. as before, but we'll leave this as this is. But if you cube negative x, you get negative x cubed, which is what's happening over here. We're starting off with the x values, the y values, and then we're reflecting it over the x-axis, which means the graph starts out as normal, and then we reflect it vertically. So we're changing outside, which is changes to the y values. A vertical stretch by a factor of 4 means we start out with the y value as it is, and then we're going to multiply all the y values by 4. But a horizontal stretch by a factor of 4 is counterintuitive. If we want to have a horizontal stretch by a factor of 4, I can't multiply by 4. I have to divide by 4. This actually means a horizontal stretch. It's counterintuitive. Whatever I multiplied by, the stretch is indicated by the reciprocal of that number. So in this case, since I'm trying to stretch by a factor of 4, I'm really supposed to multiply by the x values by 1/4. Now let's see what's going on with this answer here. They say we find the function after going through each of these processes. So we start out with square root of x. What I'm going to do is show the steps of the first 2 steps in green and then the final step in blue. And we do what they say to the previous step. So first step is shift up 2 units. Shift up 2 units. So that means the new graph is going to be y equal to the square root of x. And then we add 2 to that because since it's an upward motion, we add to the whole function. Then we're going to take this function and do whatever else they say to do to that. So now we're going to reflect that whole thing about the x-axis. That's a vertical transformation. So now my new function is going to be y equals to negative of the whole original, the whole function from the previous step, not the original, from the previous step. And then we're going to take that, let's see what that works out to be. That works out to be y equals to negative of x minus 2. Then I'm going to take that, this guy, and do what they say to the final step, which is reflecting about the y-axis, which means a horizontal motion, which means all my x's are going to be replaced with negative x. And this is the final result. Going through step by step, that is my final result. Number 28, and I encourage you to try some of these questions on your own and see if you get the same answer that I get. Number 28, first we're going to reflect it over the x-axis. That means we're going to do a vertical transformation. It's going up, down. So we have y equals the negative of square root x. And again, the reason for that is it's a vertical transformation. It's a reflection over the x-axis. Then we're shifting to the right 3 units. Since we're shifting to the right 3 units, what we're going to do is take our x values and change that by subtracting 3 from the x's, because it's a horizontal transformation and they're typically counterintuitive. They do the opposite. And then the final step, which we take from the previous step, is to shift down 2 units, which means we take the step that we've just completed, and then we're going to go downward 2 units, subtract 2 from the whole thing. And that is my final result. Now let's go on to the next step. Next question here, number 29. Starting out with square root of x. And let me just do a little adjustment here just so that we're clear about the questions that we're doing. So in this case, we're reflecting about the x-axis just as we did above. So again, we start out with the x-axis and then we're doing a vertical transformation. So that will mean that we have y is now equal to negative square root of x. Then to that, we're going to shift up 2 units. So I'm going to add to the whole thing plus 2. And then from this, we're going to shift to the left 3 units. So that result now is going to be y equal to, take my x values and add 3 to that x values, and then I'm going to add 2. So you may also write this as y equals to 2 minus square root of x plus 3, because we just wanted to put a positive first. Doesn't matter which one you do, they are both the same expression, so this is fine. Just make sure you're clear about that. Now, number 30. In this case, we're shifting up 2 units first. So we start off by taking our function and adding 2 to the whole thing, because we're doing it what is expected. Then we're reflecting about the y-axis, which means that's a horizontal reflection, because the y-axis is a vertical line, and if you're reflecting it above the y-axis, then you're reflecting horizontally that way. So then that means all our x's get replaced with negative x. So we have y equals to square root of negative x and then plus 2. And then from that, we are going to shift left 3 units. Now we have to be very careful about this. With this one, what we're going to do, since we're shifting left 3 units, we're going to replace all our x's with negative x. Now there's a negative in front of the x here already, so I'm going to put the, sorry, not replace x with negative x. I apologize for that. We're going to add 3 to all my x values. So since I have a negative x here, I'm going to take that x and put x plus 3 in parentheses, with the negative still remaining in front. And then we have the plus 2, and that is our resulting expression. And I'm going to also rewrite that expression another way that you may also see it. And that way is in this form: y equals to the square root of negative x minus 3 and then a plus 2 on the outside. What I did was I distributed the negative under the radical. So you want to be very careful about how you approach those types of questions, because you need to make sure you factor out a negative 1 before you do your transformations if you're going to do this. Now let's try this series of questions here. So let's take a look at these questions. Suppose that the x-intercepts of a graph y called f of x are -8 and 1. So those are the x-intercepts. Those are where the graph crosses the x-axis. Let's ask ourselves, what happens? What are the new x-intercepts now if we have graph y equal to f of x plus 4? Now, if you notice, y equal to f of x plus 4 really means that this graph f of x is shifted to the left 4 units. So the new x-intercepts then will also be to the left. So it would be -8 minus 4, which is -12, and 1 minus 4, which would be -3. So the new x-intercepts will be at -12, 0 and -3, 0, because we shifted the whole graph to the left 4 units. So similarly, if we shift the graph to the right, if we have f of x minus 3, now we're taking the f of x graph and we're shifting it to the right 3 units. So the new x-intercepts are going to be 3 units to the right of the original x-intercepts. So we have -8 plus 3, which will be -5, and 1 plus 3, which will be 4. So the new x-intercepts are at -5, 0, and 4, 0. Now, if we multiply all our x values by 2, or if we multiply our y values by 2, all we're doing is saying, we're multiplying our output by 2. The x-intercept gives you an output of 0. When you multiply 0 by 2, you still get 0. So your outputs are gonna be the same. So we have the same x-intercepts that give you 0 as an output. So we're still gonna have x equal to -8 and x equal to 1. Now, if we replace all our x's with -x, then the graph is going to be reflected about the y-axis. So we have a reflection about the y-axis. That means all our negative x's are now going to be positive, and all our positive x's are going to be negative. So the new x-intercepts are going to be the opposite signs. They're now going to be 8 and -1. So there will be, while the graph originally crossed at -8, 0, now it will cross at 8, 0. And while the original crossed at 1, 0, now it will cross at -1, 0. And there you have it. Now, let's talk about the next part here. What if the graph is decreasing on the interval from -2 to 7? Now, to illustrate what we're doing here, we're saying that the graph is going downward. Let's just use a little line segment to illustrate what's going on. Downward from 2 to 7. So from x equal to 2 to x equal to, from x equal to -2, sorry, to x equal to -7, to +7. So just to illustrate what's going on here, we're just using just that interval from -2 to +7. Now, over what interval is the graph of y equal f of x plus 2 decreasing? Now, if I do y equal f of x plus 2, and think about this a minute, what are we doing to the graph of f of x? What we're doing is we're taking the graph of f of x and we're shifting it to the left 2 units, which means the interval also gets shifted to the left. So the function is now decreasing on an interval that's 2 units to the left of the original interval. So it's decreasing on an interval from -4 to 5, because we start at -2 and shift it to the left 2 units. We start at 7 and shift that to the left 2 units. So now we're going from -4 to +5. Part B. On what interval is the graph of y equal f of x minus 5 decreasing? Again, very simple. So y equals to f of x minus 5, again, simply means that the graph of f of x is now shifted to the right 5 units. We're shifting the graph to the right 5 units, which means the interval on which the graph is decreasing is also shifted to the right. So we say that the graph is now then decreasing on the interval we're going to move -2 5 units to the right, that lands us at 3, and we're going to move 7 5 units to the right, that lands at 12. So that's the interval on which the graph is decreasing. Now for part C, what can be said about the graph of y equal to negative f of x? When we do y equal to negative f of x, we're reflecting about the x-axis. So we reflect over the x-axis. It's a vertical reflection. So that means whatever was going downward is now going to go upward, and whatever was going upward is now going to go downward. So the graph will now look like this. Over the same interval. So the graph is now increasing. And even if it crossed the axis, it will still revert to the original thing. So the graph is increasing on the same interval from -2 to 7, because all we changed was the y values. All the positives became negative, all the negatives became positive. Now, if we do y equals to f of negative x, what we're doing is reflecting over the y-axis. So now the graph looks something like this. Imagine that there was a y-axis here. When you reflect it, what was over here goes there, whatever on the right goes to the left, so the graph is going backwards like that. However, the deal is the -2 is now going to be a +2, and the +7 is going to be a -7. So what is happening is that the graph is still increasing, but it's increasing in an opposite order. So the graph is now increasing, but on the interval from -7 to +2. So when we reflected it over the y-axis, what was decreasing is now increasing, but when we reflected over the x-axis, it's just increasing in the opposite order. Now, this is not a standard rule. You need to draw the graph to see what's going on to help you to have an idea of how all of this works. If you don't do that, you'll run the risk of making a serious error, which you do not want to do. It's best to visualize what's going on and make the necessary adjustments than to just try to do this in your head. All right, let's go on to our last set of examples here. I believe, we have 2 sets here, 2 different graphs. So this one will take some focus here, so you want to pay close attention to how we're doing this. In this question, what we're trying to do is draw the new graph. We're trying to draw the new graph based on the given graph. And let me just quickly check how many examples we have. 2. And then we have another set of examples here. So let's go on and start off with this set right here. So we have this piecewise defined function. And for part A, which is not exactly in the, I think I just made an error here. Let's back up. For part A, which is not exactly under its spot, part A is for the capital f of x function. This says just take f of x and shift it up 3 units. So now we go from -4, -2, up 3 to -4, 1. And then we go from 0 to up 3 to 0, 5. 2, 2 goes up 3 to 2, 5. And 4, 0 goes up 3 to 4, 3. and then we just join them with our little line segments. Having a little difficult to join my line segment here. So our new points are -4, 1, 0, 5, and 2, 5, and 4, 3. Now we look at part B. Okay, now part B. In part B, we are shifting the graph to the left 2 units because we're having x plus 2 and it's counterintuitive. So everything gets shifted to the left. So the -4 gets shifted to the left to -6. The y coordinate is still the same. The 0 gets shifted to the left to -2. The y coordinate of 2 is the same. The 2 gets shifted to the left. And the 4 gets shifted to the left to 2 units right there. And there we have it. And then, of course, we use our ruler or a straight edge and your pencil and join the line segments. And what we have is the new graph. This is the graph of a g of x, capital G of x equal to f of x plus 2. And this graph was capital F of x, which is equal to f of x and then plus 3. Now for graph C, we're just doing negative f of x. So p of x is equal to the negative of f of x, which means all the parts below the x-axis are now going to go above, and all the parts above are going to go below. The y values stay the same because we did a negative outside of f of x. So we go from, the x values are going to stay the same because the y values are what's going to change. So -4 stays the same, but -2 becomes +2. 0 stays the same, but +2 becomes -2. And then the points on the axis don't change because when you multiply a negative number when you multiply 0 by a negative number, you get the same thing. You get 0. So 0 does not move. And there you have it. And of course, you can fill in the corresponding points. So this point is -4, 2. This point is 0, -2. And of course, 2, -2. And 4, 0 stays the same. And over here, we had -6, -2. And then -2, 2. And 0, 2, and 2, 4, because everything got shifted over to the left. Now part D is f of x plus 1 and then -2. That's our function h of x is equal to f of x plus 1 in the parentheses and then -2. Now the plus 1 in the parentheses means you're shifting the graph to the left 1 unit, and the -2 outside means you're shifting down 2 units. So the -4 is going to go to -5, and the -2 is going to go down to -6. So our new point is -5, -6. And then 0, 2 is going to go to the left and down. So it's going to go to -1, 0. And then 2 is going to go to the left 1 and down 2. And that's going to go down to 1, 0. And then 4, 0 is going to go to the left and down 2. So it's 3, -2. So we just do a shifting to the left 1 unit because that's what happened with the x-axis, the x values. And then for the y values, we're shifting down 2 units. So my new values are going to be -5. Oh, I think I made an error here. Let me correct that. I go to the down left negative and down 2, so it should be -4. Apologize for that. So it should be -5, comma -4. Little error there. That is corrected. So now let's draw the line segment. There we go. And then this graph point here is now at -1, comma 0, and that's at 1, comma 0, and that's at 3, comma -2. Now for part E, half of f of x. That means you're multiplying all the y values by half, and that graph is q of x. Is equal to half of f of x. So let's see what that gives us. All right. So what we're going to do is multiply all of our y values by half, but our x values are going to stay the same. So -2 is now going to go to -1, but my y value is the same. 0 is still going to remain at 0. 2 is going to become 1 for the y values, that is, but the x values will be the same. And so our whole graph is going to be compressed to half of its original size vertically. So this is a vertical compression. So we have -4, comma -1, 0, comma 1, 2, comma 1, and 4, comma 0 didn't change because when you multiply 0 by half, you get 0. Now let's take a look at f of -x. So this is lowercase g of x is equal to f of -x. And all that does is reflect the graph about the y-axis. So everything on the left goes to the right. So the -4, -2 becomes +4, -2. And the point right here, which is -2, 0, becomes +2, 0. And 0, 2 remains the same place. And 2, 2 becomes -2, 2. And 4, 0 becomes -4, 0. So all that happens is the graph gets reflected about the y-axis, and all my positive x values become negative x values. So we have 4, -2, we have 0, 2, we have -2, 0, and we have -4, 0. And then let's take a look at h of x is equal to f of 2x. And what this is saying is we have to double the x values before we plug them into the function, which means the graph is going to get a horizontal compression. So I'm going to take all of my x values and cut them in half. So -4 is going to become -2, but the y value will stay the same. -2 has become -1. 0 is still going to be 0, but 2 is going to become 1, and 4 is going to be 2. So the graph now is going to be compressed to half its original size. And so it's squeezed in. And remember, this is because when you make changes to the x's, it becomes a counterintuitive experience. And in this case, the y values do not change. So this is now 1, 2, This is still 0, 2, and this is now 2, 4. And there we have that example completed. Let's move on to the next example. Okay, next question says graph each function using the techniques of shifting, compressing, stretching, and or reflecting. Start with the graph of the basic function, for example, y equal x squared, if that's the basic function, and show all stages. Be sure to show at least 3 key points, find the domain and the range of the given function. So what I've done here is I have created 3 preliminary graphs and then the main graph grid at the bottom, so that you will see the process through which I go to get the final graph, or the resulting graph. So we're going to first identify what our basic graph is. That's what I'll graph first. In this case, the basic graph is the x cubed graph, because as you see, it's just a variation of x cubed. And the x cubed graph starts, it looks like this. That's basically what it looks like. And in this case, as you can see, there are just 2 steps that we're going to do. One step is to shift the graph to the left 2 units, and the other step is to shift the graph downward 3 units. So when I shift the graph to the left 2 units, the graph gets shifted over. Having a little difficulty here drawing my graph, but you get the idea. And then once I shift it over 2 units, then I'm going to shift it down 2 units. So now the graph, and one of the ways you can know where it's going to cross the y-axis, if I plug in 0 for x, then I will see that the answer works out to be 5. So the graph is going to basically do something like this. So the resulting graph then, which I will draw beneath, this first graph here is y equal to x plus 2 cubed, and this graph is the graph which I'm looking for, is y equal to x plus 2 cubed and then minus 3. So at this point here, that would be a point -2, because I shifted it to the left. And at this point here, if I were to plug in 0 into the function, this would have been 8. So now when I go down to the final graph, then I know that the graph should look like this graph, although probably a little neater. I'm going to try my best to draw it so it looks a little neater. It is a horrible looking graph, but you get the idea of what I'm trying to do here. This point is the point that we get when we plug in 0 for x. So f of 0 would be 0 plus 2 cubed minus 3, and that will give us 5. So this point is the point x equal to 5. Now if I set y equal to 0, then I have x plus 2 cubed minus 3, and that would mean I would add 3, and then I would take the cube root of 3, and then I would subtract 2 from that, and that would be my x value. So that's not a very nice point to identify, because it's a weird irrational number. It's a cube root of 3 minus 2. That's the actual x coordinate right there. But this point here was started out as this point up here. That point is a result of shifting the graph 2 units to the left and then 3 units downward. And we can always just identify one more point if we wish. If we plug in, say, -3 into the graph, I go f of -3, I would get -3 plus 2 cubed and then minus 3, and that will just be -4. So when I plug in -3 here, the answer would be -4. And there we have it. So that's my result there. For this graph, as you can see, the graph we're starting out with is the x squared graph, which looks something like this. Again, not drawn to scale, but I'm going to try my best to draw it the most smooth way possible. And again, with this one, we're going to stretch the graph, then we're going to shift it. So first I'm going to stretch the graph by a factor of 3, so it's going to be narrow. It's going to be stretched higher. So this graph now is y equals to 3x squared, and I forgot to write that this is y equal to x cubed. So this is y equal to x squared because that is, of course, the original function. Then the next step is to shift this graph to the right. And so when I shift this graph to the right, I'm going to get this point here will be 2. So this is the graph of y equal to 3 times x minus 2 squared. Now that graph is going to be shifted down 2 units. Now, to point out here a few things here, if I plug in 0, so f of 0 would be 3 times 0 minus 2 squared plus 1. So that would be 3 times 4 plus 1, which is 13. And so when I shift the graph, oh, sorry, this graph won't be shifted downward, it will be shifted upward. My apologies. So when I draw the graph, again, not drawn to scale, but this point here represents the graph going 2 units to the right and 1 unit upward. This point represents the y-intercept. So when I plug that in, that point is 13. And if I plug in, say, f of, choose a point to the right of that, let's say we plug in f of 3, I get 3 times 3 minus 2 squared plus 1, and that just gives me 4. So f of that point there would be 3 comma 4, and of course that point again there is 2 comma 1, and there we have it. Now with this graph here, they want us to start off with the square root graph. The square root graph because it's the square root of some stuff, so I'm just gonna draw the square root graph there. Again, not drawn to scale, but just to give an idea of what the graph looks like. So that's the graph of y equal to square root of x. In this case, we're gonna multiply everything by a factor of 2, so the graph becomes actually taller. And again, not drawn to scale, I'm gonna try to make a little adjustment here just for the sake of the notes. So that would be y equals to 2 times the square root of x. And then I'm going to shift the graph to the right 2 places because of the x minus 2 under the radical. And trying to make it a little smooth here. And that is the point 2. So that's a y equal to 2 times the square root of x minus 2. And then add 1 to that. So this whole thing gets shifted up 1 unit. And I'm going to use a different color here. So this point now is going to be the point 2 comma 1, and then we can start plugging in some numbers. So of course, if I plug in 0, that will give me no solution because the domain is now from 0 to infinity. So we have if I try f of say 3, then that will give me 3 minus 2 is 1, 2 times square root of 1 is 1, 2 times 1 is 1, 2 times 1 is 2, 2 plus 1 is 3. So that point would be 3 comma 3. And so that I get a square root under here, I'm going to then do f of 11. And f of 11 would be 11 minus 2, which is 9. Square root of 9 is 3. 3 times 2 is 6. 6. Well, apparently I can't go as far as I want. So instead of using 11, let's do f of 6. f of 6. 6 minus 2 is 4. Square root of 4 is 2. 2 times 2 is 2. 2 plus 1 is 5. So if I plug in 6 here, then this point would be 6 comma 5. Now, there's something I neglected to point out, the domains and range of the resulting function. So for these first two, this first function here, the domain is all real numbers. As you can see, it goes from left to right. And the range is also all real numbers because it goes from bottom to top. In this case, the domain is all real numbers because it goes all the way to the left and all the way to the right. But the range has the graph has a lowest point, so the range goes as low as 1 and goes up forever. In this case, the domain, it doesn't go all the way to the left. It starts at 2 and then goes all the way to the right. And then the range graph starts at 1 and goes all the way upward. Right there. So that's the domain and the range. And let us do a few final examples here, and then we will call that the lesson. Now, in this case, again, we're starting out with the square root graph. So I'm going to draw a little sketch of the square root graph. Let's draw it in red this time. I'm going to draw it a little bit slimmer because of the multiplication. So that's the graph of y equal to square root of x. Then this thing says multiply that by 4 and then multiply by -1. So I'm going to do both steps. I'm going to multiply by 4, so the graph looks kind of like that. So that's y equals to, let me use the green here. So that's y equal to 4 square root x. And then when I flip it upside down, because of that -1 on the outside, then the graph is now y of -4 square root x. And then the final step, which I will draw in blue, is to shift the graph to the right 1 unit. So the graph now will look like this. So the graph, as you can see here, the domain of this function and I'll try to put it right here. The domain of this function is from 1 to infinity, and the range of this function is from -infinity to 0 because we start from the bottom upward. This is the overall graph. Y equals to, put this over here, y equals to -4 square root of x minus 1. Couple of points in question. We shifted over to the graph to the right, so it's 1, 0. And if you plug in, say, if you plug in 0, that will give you no answer. And if you plug in 1, you get 0. If you plug in 2, you get -4. And then if you plug in 3, you get 3 minus 1, which is square root 2, which is a difficult thing to work with. So let's plug in 5 instead. If we plug in 5, we get 5 minus 1 is 4. Square root of 4 is 2. 2 times -4, it's -8. So if I plug in 5, I should get -8. There we go. Now let's try this one. Now this one we'll need to do a little bit of adjustment first. What we'll do is we'll do what I said on a previous slide. We'll rearrange this so it's -x plus 1. I just move these backwards. And then that means g of x is actually equal to 2 times the absolute value of see what we have here. G of x is equal to 2. Well, let me do this. Let us write this as g of x is equal to 2 times negative x plus 1. And then that will give us g of x is equal to 2 times the negative of x minus 1. I factored out the negative 1 there. Now it's kind of interesting because absolute values are even functions. So the absolute value of a negative is exactly the same as the absolute value of a positive. So I will actually get 2 times the absolute value of x minus 1. It's the same thing as the one above. So I only have to do two things. I start off with the absolute value graph. And then multiply the whole thing by 2. So that means the graph goes upward to twice as its rate. And then we're going to shift the whole graph to the right. And that's what I will draw as a final product down below. And of course, if I plug in 0 for x, I will get 2 for y. Since I shifted over to the right 2 units, then this point here is at 1. And again, if I plug in, let's say I plug in 2 for x, so g of 2 would simply be 2 times 1 minus 2, absolute value of 1 minus 2. And that's just going to give me 2. So the domain of this function is all real numbers because it goes all the way to the left, all the way to the right, and there's no break in the graph. And the range is the lowest value of this graph is at 0, the lowest y value, and it goes up to infinity. Now, let's go on to the last example here. This one is not an even function, so the transformation is really going to matter here. What we're going to do is rearrange this as negative x plus 2. And then I'm going to factor out the negative 1. So g of x is equal to 4 times the square root of negative parentheses x minus 2. Which means in this case, I'm going to multiply the graph by a factor of 4, then reflect it about the y-axis. So the original graph starts out like this. And because I'm going to need to multiply by 4, I'm going to draw it a little bit narrower. So that's the graph of y equal to square root of x. And I forgot to put that this is the graph of y equal absolute value of x. This graph here was the graph of y equal to 2 times absolute value of x. And this graph down here is my ending function. G of x is equal to 2 times 1 minus x. Absolute value 1 minus x. Now, over here, the first thing we want to do is multiply the whole graph by a factor of 4. The next thing we want to do is reflect it about the y-axis because of that negative. Actually, I'm going to shift it first because of the parentheses. So I'm going to shift the graph over to the right 2 places because PEMDAS says do parentheses first. So it's the graph of y equal to 4 times the square root of x minus 2. And then I'm going to Oh, I'll have to correct myself here. First, I'm going to reflect it. Reflect it about the y-axis, and then I'm going to shift it over. So this is the graph of y equals to 4 times the square root of negative x. And then my final graph is to shift that whole thing to the right 2 units. So that's what it should be there. And then when I shift the whole thing to the right 2 units, our graph looks like this. Now let's check to see if we are correct here. If I plug in, since I shifted it 2 units to the right, then this point is at 2. Then if I plug in 0 for x, then this point becomes 4 square root 2. And then if I plug in, say, negative 2 for x, then this point becomes, if I plug in negative 2 for x, then this becomes 8. So the domain of this function is negative infinity up to positive 2. And the range of this function is from 0 to infinity. And this is the graph of g of x equal to 4 times the square root of 2 minus x. Let me just clarify something here. Up here, what we did was first we multiplied the whole graph by 4. And since I factored out a negative 1 here, this becomes x minus 2. I do the multiplication transformations first. So I multiply by a factor of 4 and reflect it about the y-axis. And then I shifted the graph over to the right. If I did it the other way, I would have gotten the wrong graph, and that would have been a problem. And to illustrate with that I'm correct here, I have a little function here. Let me just switch my my calculator settings here, and that I click y equals, and I do 4 times the square root of 2 minus x. And let's make sure our window is appropriate. Let's go from negative 10 for the minimum x value to positive 10 for the maximum x value. And then for the minimum y value, we go from negative 1, and let's say we go up to 10. And let's see what that graph looks like. Relatively similar to what we have. It's kind of a lot steeper than mine, but same idea. So that brings us to the end of this lesson. Of course, there's a lot of practice that you'll need to do, and I encourage you to make sure you do that. And of course, as always, I strongly recommend that you use Khan Academy as a resource both for additional videos and for practice. And additionally, you can also use your textbook and the website openstax.org, openstax.org, and they have college algebra books for free online, and there's also an app for Android. All the best, keep practicing, keep studying, keep working.